Okay, I'm inferring that you're supposed to be proving this trigonometric identity right here, that the left side is always equal to the right side, as long as the denominators are not equal to 0. So here's the original problem, written with this symbol right here instead of an equal sign, which implies that these two expressions are strictly identical. Usually when you're proving a trigonometric identity, you don't want to change one side of the identity. You want to work on one side and make it look like the other side. Usually you choose the more complicated side and make it look like the simpler side. In this case, both sides seem to have the same level of complexity, so I chose to use the right side. And what I notice is this is a common theme when you're proving trigonometric identities, is that if you have something that looks like this, 1 minus the cosine of something, if you multiply by 1 plus the cosine of something, you'll get a difference of squares. And you'll see what happens after you do that. So I'm allowed to multiply top and bottom of this fraction over here by 1 plus the cosine of 2x because this is equivalent to the number 1. Any number divided by itself is 1. And so here's the new numerator, sine of 2x times 1 plus the cosine of 2x. But in the denominator, I get a difference of squares because I'm multiplying the sum and difference of the same two numbers, or trigonometric expressions. But 1 minus cosine squared is sine squared. And that's from the trig identity, sine squared plus cosine squared equals 1. This is just another form. And now here's what happens. I've got two factors of sine of 2x in the denominator, 1 in the numerator. So one of these cancels out. And now in the new, oh, and by the way, I use the commutative property for addition to change the order on these two terms so I would match the left side. And after I cancel out this common factor of sine of 2x, they're identical. Okay, so I have proven that this is a trigonometric identity. It's not just a trigonometric equation. It's true for all values of x for which the expressions are defined. So there you go, QED, that which was to be proved. Hope that helped. If you have any questions, post a comment.